Hi everyone, welcome to another video on using Excel. Today we'll be extending our analysis to the probability in normal distributions. There'll be three main topics that we'll cover. The normal distribution function or the Norm.dist function for generating the PDF. The Norm.dist function for CDF or cumulative distribution function. And finally we'll be looking at the inverse function, the Norm.inv, as a reverse of CDF. In case you're not well acquainted with probability distribution function and cumulative distribution function for normal distributions, there's no need to worry. We'll look at a conceptual understanding of what these really mean. Finally, at the end, we might just look at another additional function that is commonly utilized along with these three functions within Excel when dealing with the probability of normal distributions. So let's begin. The PDF or the probability distribution function is something that we have covered in a previous video as well. So I'll leave a link at the top. It's also known as the probability density function, or commonly abbreviated as PDF. One very important thing to bear in mind when dealing with the PDF function is that its primary and legitimate use is for discrete data only. Now, what is discrete data? Now, discrete data is generally something which you can count. In other words, if you can apply any known natural number system mapping to your data set, then you're dealing with discrete data. Also, keep in mind that discrete data can generally be of two types. You can have finite discrete data, and you can also have countably infinite discrete data. So when you're looking at the PDF, what does it really mean? The PDF function gives you the probability density at a specific value of X. Since you're dealing with discrete data will have a specific point, say like marking points on a number scale. And if you want to find out the probability density at a specific point, that's where PDF or probability density function is used. For instance, if you look at the graph on the screen right now, you'll see a red colored column on the graph. So let's say if we want to find the probability density for that value of X, that's what the PDF will return. The height of the column gives you the probability, and the value of that column on the X-axis, that's the value of X for which you're trying to find the probability. The other important probability concept that you'll need to know in regards to normal distributions is cumulative distribution function. Unlike the PDF, the cumulative distribution function or the CDF is used for continuous data. And within the CDF, also bear in mind that some texts will refer to this as the probability mass function also. So it can vary from text to text. Some will just call it the CDF, some will call it probability mass function. Now, what does the CDF return? Unlike the PDF or the probability density function that we are looking at, which returns probability density at a specific value of X, the cumulative distribution function gives us the probability for all points equal to and less than X. If you look at the graph, you'll see if we were to apply the CDF function to the value of X as 0, you'll see the entire area to the left of X on the graph is marked as red. So if you apply the CDF, that's what you will receive. You'll receive the probability of the value X and all the values less than X as marked in red on the graph. And that's a big difference. This is why when you're dealing with continuous data, you'll use cumulative distribution function, because you cannot apply, or you shouldn't apply, the probability distribution function to continuous data. Now, why is that? The reason, and that reason is important for us to understand, since continuous data has infinite points within any range. I mean, given any two data points for continuous data, you will always find another data point which lies in between those two data points. In other words, the number of points is extremely large. It is uncountably infinite. You will not be able to map it to a natural number system. And as a result, there will be so many points that the probability at any single given point will be near zero, or you can take it as zero. As a result, the concept of PDF or probability density loses its meaning in the realm of continuous data. Hence, we will always rely on cumulative distribution function or CDF. Now, just to remind you, in a previous video, we have looked at area left of a given point. I'll not tell you what that is for right now. If you've seen that video or if you've dealt with that topic in the past yourself, I'm sure you will be able to correlate with the concept of area to the left of a point for a normal distribution. So let's look at some actual formulas in action. So we'll begin with a standard example that we've used in the past. Let's say there's a certain university, students take an exam, and the mean score in that exam was 60 marks and the standard deviation was 10 marks. In order to generate an approximate range of the data distribution, we start with the minimum value. As you can see, the minimum value out here that we have taken is the value of 30. And how did we arrive at that value of 30? The way that we arrived at that value of 30 is we know that roughly 99% or almost the entire data set lies between plus and minus 3 standard deviations. So if our mean is 60, and if you want to find out the least point of that distribution, so basically it's the mean minus 3 times the standard deviation of 10, which gives us the minimum value of 30. That's what you see here. Correspondingly, also the maximum value will be the mean plus 3 times the standard deviation. Just like for the minimum, you have done mean minus 3 times standard deviation. For max, you will do mean plus 3 times standard deviation. So you will see that again in this, the distribution ranges all the way from 30. If you were to scroll down to the bottom, you'll see it goes all the way from 30 to the value of 90. So we're just trying to mimic the data points in a different distribution. One caveat, remember that while we will be using this distribution for understanding both PDF and CDF in action, again, remember that the PDF is to be applied for all the discrete data sets and the CDF is for all the continuous data sets. Okay, so having said that, let's proceed. So with the score of 30, we know how to calculate the z-score. The z-score is nothing but the equivalent value of this number here. So the equivalent value of 30 when measured in terms of standard deviations from the mean of the data set. So that's the formula. As you can see on the formula bar, it'll be that data point minus the mean divided by the standard deviation. So the z-score of 30 is minus 3. The z-score of 31 is minus 2.9. What does that minus mean? Remember, the minus means that this data point is towards the left of the mean. And when you start to see positive z-scores, that implies that now we have moved beyond the mean to the right. And every point to the right of the mean will have a positive z-score. Let's revisit PDF. PDF is something that we have used in the past. So how is the PDF used? If you see the formula there, it is Norm.dist followed by the value of X or the value of the corresponding z-score if you're using a standardized normal data point, comma 0. The 0 here represents the mean of that standard normal distribution. Remember, every normal standard distribution has a mean of 0 and a standard deviation of 1. We have covered this before. Again, I'll leave a link to a prior video where we have dealt with this. Comma false. That false is nothing but it's a reference to the fact that we want to calculate the PDF. Remember that the default functionality of the Norm.dist is to generate a cumulative distribution function. In that case, you use the fourth parameter as true. On the other hand, if you want to generate the probability density or the probability distribution function, please use the fourth parameter as false. So having said that, when we use the Norm.dist function to generate these values, this is what you get. Remember what this means. Each of these numbers that you see in column C under PDF represents nothing but the probability at that specific point. So 0.44% is the probability density of minus 3 in this distribution. That's the implication. That's the meaning of this. All right. So if you look at the graph on the right hand side, for instance, if we were to look at the PDF value for the z-score of -1, so let's scroll down, let's see. The z-score of -1 is given here as 24.197%. So if you see the red colored column on the graph, that red colored column, or rather the height of that red colored column, represents the probability density at the point -1. As you can see, the height of this column is 24.197. 24.197, that is the probability density at the point -1. That is how this is to be interpreted. All right, let's go on to CDF. Now, CDF is not something that we have covered before, except for the brief introduction to it that we looked at the first page. So within CDF, remember that the CDF is primarily used for continuous data. The way it is applied in function format in Excel is Norm.dist. The first parameter, or B12, as you can see here, is the value of X. The second parameter is the mean. The third parameter is the standard deviation. Since we are using the z-scores here, your mean is 0 and your standard deviation is 1. And the fourth value of the parameter we are taking is true. Why? Because that's the default functionality. If you take true, it will generate the cumulative distribution function for us, or the probability mass function, as is also known. So what does this intuitively mean? So if you want to understand this graphically, in order to do that, let's take a look at the value of CDF for -1. So for the z-score of -1, we see that the CDF is 15.866%. So we'll just keep that in mind, 15.866%. And now let's scroll down and take a look at the graphical representation of this. So this here is a cumulative distribution function graph. On this graph, here is where you have the -1. And you will see that the entire area to the left of -1 is coded as red. So, and that's what we receive. The cumulative distribution function gives us the probability, or the area to the left of the curve, or rather to the left of that point, all the way from the beginning till that point. So again, a quick reminder, the CDF tells you the probability at the point X and all the values of X to the left of that point X. In other words, this is area. So that's a good comparison for the PDF versus the CDF. Okay, let's move on to the next important thing. So the next important thing that we have here is a derived z-score. Now, what derived z-score column tells us here is, given the value of CDF, how do you arrive back at the value of X? So here, the formula that you will be using is the Norm.inverse formula. What the Norm.inverse formula in Excel does is that it takes the probability value and then along with that takes the mean, which is 0, and the standard deviation, which is 1, and gives you back the z-score that you started off with. In other words, given a certain value of probability for a normal distribution, given its mean, given its standard deviation, it will tell you the exact point at which and before which, if you add up all the area, you get the CDF of, let's say in this case, 0.135%. Right? So basically, going back to the graphical distribution, if I give you the value of this red colored area, and if I give you the mean and the standard deviation of this distribution, you will be able to arrive at -1. So this is the inverse of your cumulative distribution function. That's a very helpful formula. Finally, let's take a look at one more thing. We have the Z table value. Now, the Z table value is something we covered on the video of using Z scores and the Z tables. So basically what we have put here is, for each of the z-scores here, we've put the corresponding z-table value here. How's that done? Again, for example, it is -3 out here, the z-score. If we were to go to the z-score table and look at -3, there we are. You see for -3, the value is 0.00135. So that's why you have 0.00135. Let's look at -2.9. So for -2.9 is a z-score. Again, -2.9, there we are. It is 0.00187. So it's again 0.00187. Okay, that's what we have. So what is the relationship here? Now the relationship here is, if you notice, the values that you have in the z table, the values that you can look up from the z table, you can derive the same values from the CDF. And that's relationship that we spoke about earlier. Remember that when you're calculating the z table value, what are you actually looking up? So whenever you look up the z table value using a z-score, what you're doing is you're finding out the area to the left of that point. And remember, that's what CDF does as well. So no wonder whatever value you find from looking it up on the z table is the same value that you'll get by using the Norm.dist with the fourth parameter as true. So the CDF function and the z table values are the same. It might look slightly different, but that's because this one is in percent format and this is purely in decimal format. But if you were to just quickly convert this and adjusting for decimal places, there you are. If you look at it, you'll see all the values here are exactly the same as the values here. So that's another important observation, important thing to bear in mind, that you can look up these values from the z table. If you don't have Excel, if you have Excel, it's far more easier to just apply the cumulative distribution function to arrive at the z table value. Before we move on, one last thing. There is another helpful formula within Excel. This formula is called Standardize. What the Standardize does is basically takes a certain data point and returns the corresponding z-score. So you can already manually calculate the z-score for any data point by using the known formula, but you can also use Standardize. So for instance, here we are calculating it manually, but if I don't calculate it manually, I can also use a Standardize function. So let's see how that works. So if I was to use Standardize, let me just increase the font size here. Okay, so how does it look like? So the Standardize function has the following parameters that it takes. It takes x here meaning, for example, 30, the data point, the mean and the standard deviation. So if once I give it the input of the data point, the mean and the standard deviation, it should return the z-score. So let's try it out. So let's say the x is 30. The mean, as we know from the problem statement, is 60 and the standard deviation is 10. Let's see what it returns. There you are. As you can see, it has returned -3, which matches the z-score. Let's try it for one more case. So let's say we were to apply it on... So let's say we were to apply it on 32. So if you were to apply it on 32, and the mean is again 60, and the standard deviation is 10, let's see what do we get. We get -2.8. As you will see, for 32, that's the value, -2.8. So yeah, this is again a useful thing to keep in mind, though you can always compute it manually, but if you want to use Standardize, you can use that as well. So now let's rewind back and understand what we've just looked at. So what we've looked at right now and what you were seeing on the columns is we started off with a given data point. From that given data point, we arrived at a z-score. If you want to use a manual formula, then remember this is the z-score formula that's mentioned here. So basically, using this formula from the data point, you get to the z-score. Alternately, you can also use the function Standardize. Once you have the z-score, what you can do is you can do a couple of different things. If you want to calculate the probability density specifically at that point, then you can use the Norm.dist function. With the fourth parameter as false, it will give you the probability density function value. On the other hand, if you want to arrive at the probability mass function, or the cumulative distribution function also, as it's called, then you can use the Norm.dist function with the fourth parameter is true. It will give you the CDF. Once you have the CDF value, or the CDF function value, if you want to arrive back at the data point or the value of X, which gives you that cumulative probability, you can use the Norm.inv or the Norm.inverse function, which will take in three parameters. It will take the probability value, the mean, standard deviation, and you will come back to that data point. So conceptually, keep this in mind. This is how you traverse within the data up to the z-score, the CDF, back to z-score, or if you need the PDF value, if you're dealing specifically with a discrete series or discrete data series, then you can use the PDF instead. Now, is it necessary to always arrive at the z-scores? Not really. That was just for conceptual clarity. In general, this would also work given a data point. If it is discrete, you want to use PDF, same function. On the other hand, if you're dealing with continuous data series, then you can derive the CDF. From the CDF, you can derive back the given data point. So this is what we wanted to cover finally at the end of this video, so that we have some conceptual clarity of both of these. These are again used heavily in solving different problems, whether given it's a discrete data set or a continuous data set. All right, hopefully this was a helpful and instructive video. See you next time.